I is the variable given to rotational inertia. So this is just like mass, except the rotational version, the angular analog of mass. I'm going to whip out Newton's second law here, F equals ma. We have already seen the rotational analogs of acceleration and force. So if we put those in, replacing force with its rotational analog torque, and linear acceleration with alpha, angular acceleration, this would be the Newton's second law equation, F equals ma, only this is the rotational version. We can't just put an m because that's the linear version of mass, or the linear version of inertia, but I is the rotational version of inertia. So we've changed all three variables to the rotational versions. Alright, and we could just go ahead and solve for I here, and we'd get I equals torque over alpha. But the point of doing this is to be able to look at an object and figure out its rotational inertia I just by the physical properties of that object. We've just seen that the distribution of mass in an object is really important. We've seen that the farther mass is from the center of rotation, from that axis of rotation, the higher the rotational inertia is going to be. So we might want to describe I in terms of the variable r, distance from the axis of rotation. So we can put in definitions for torque and rotational acceleration that include r. We know that torque is just force times moment arm, r, and alpha. Alright. Okay, I'm going to clear out some room to solve for alpha, so I just moved this part down here. So we can get rid of that and find alpha. Okay, we know that we've seen on a slide earlier that linear acceleration A is proportional to both the angular acceleration and the distance from the axis of rotation. That makes sense, right? Because it makes sense that the farther an object is, like out on a wheel, the faster its speed has to be, the faster its linear speed has to be. And it's also true with acceleration. The farther from the center of a wheel an object is, the faster its linear tangential acceleration has to be. So therefore it would make sense that linear acceleration and r are proportional. So if we just put this little expression in terms of alpha, we see that alpha is inversely proportional to r. So we can go ahead and put in this definition for alpha, a over r, in our equation down here. A over r, so it's fr over a over r. So it's like fr divided by a divided by r. So that actually ends up that we can bring the r back up to the top, and we get fr squared over a. So we're making a lot of progress here. We have defined I in terms of r, but we can change this around a little also. Remember Newton's second law, F equals ma. If you rearrange that, we can create an F over a here. If we divide both sides by a, F over a equals m. So the F over a here, we can actually just say that's m, and we get mr squared. And this equality was I. Because remember, we were solving for I this whole time. So we've shown that the rotational inertia of a tiny speck of mass is mr squared. But what we really want to know is the rotational inertia of an object with a whole bunch of tiny little specks of mass. So for that, you have to sum up all of those tiny specks, and that's why on the slide I is given as the sum of all those tiny specks. But don't worry, you don't have to go by hand and sum up all 8 million tiny specks of mass in an object. There's just a handy table in your book that shows how to find the sum of mr squareds for any kind of shape that you have. So the simplest one is a hoop, where every point is actually the full, every piece of mass is the full distance r from the axis of rotation. So the sum of the mr squares is just the sum of all the little pieces m, so that the mass of the full object is the big M times r squared. So that would be for something like a spinning hula hoop. But then if you have a cylinder, where you have mass distributed among the entire object at all sorts of different distances from the center of rotation, then your I value, the moment of inertia, isn't going to be the full mass m times the radius squared. It's going to be some fraction of that, and for a cylinder it's pretty simple. It's just a half of the full mass of the cylinder times the radius of the cylinder, which is from the center of rotation to the outside. And then you'll also see in that table a sphere as opposed to a cylinder, and so for this one it would be like a baseball or the head of a statue or something like that, to be kind of random. But here, for a sphere compared to a cylinder, there's more mass concentrated toward the center. So it would be even a smaller fraction of the full mass of the sphere times the radius of the sphere squared. So those are a couple examples. But there's tons of these in the table in the book, or you can probably just Google it online. But one thing to be wary of is that if you have like a rod that's spinning, it depends on where the axis is. It could be spinning around the center. So like a baton, a cheerleader throws up a baton and it's twirling in the air. The moment of inertia for this thing would be like 1/12 of its mass times its length. So here's one where you don't use R, you use L. Oops, I wrote down R. Let's correct that. But if that same baton or whatever kind of rod was affixed at one end to something and it rotated around an axis here, like this, then that moment of inertia would be different. In this case, it would be 1/3 of the mass of the rod times the whole length of the rod. Squared. These are squared. Length squared still. Okay.